Welcome back to R for Economics. In this one, we'll be looking at the likelihood of a normal distribution. The same kind of things can be used for other distributions, and it's not just limited to the normal distribution. So we're going to set our seed so that we can get reproducible results, so that when you run it, you'll get things that look exactly the same. But this is a not necessary step. So first, let's generate a normal series. 100 observations, mean 0, standard deviation 1. So that's a standard normal series. And if we look at the histogram of this, we can see that it looks pretty much like a normal distribution. Now, we can get the density of any of these points, any of these observations, by running the d-norm. So that gives me the density based on the normal distribution with a mean of 0 and a standard deviation of 1. And it's not in the log series. So if I get those, and then I plot them, I can see in my y-axis that this is the density or the probability of observing that value. So around 0 is going to be maximized, and way out at the tails, here at -3, it's going to be really low and close to 0, but still a positive probability. Now, the default is that this is actually equal to, is the default. So if I run this, I get the exact same values as I do for my H. Now, if we want to generate the likelihood, the total likelihood, what we do is we take the product, use the product function of H. So we multiply all of our observations, the probabilities that we have here, all together. So everything in this series, these dots, would end up getting multiplied together. And we run that, we end up with 5.69 to the power 10 times 10 to the power of -64, which is a really small number. So that's going to be really hard to deal with, which is why in a lot of cases we use the log probabilities. So this time we're going to take the d-norm E defaulting to the mean 0, standard deviation 1, but now we're going to say, give me the log probabilities instead. And when I do that, so now I've got the log probabilities, but you'll notice that everything is negative. And that's because any value between 0 and 1 will be a negative value. What's the benefit of this? Well, 1, 2, 3, 4 are much easier to observe. Also, when we want to get the total likelihood, we're going to take the total log likelihood. Now, rather than taking the product, the log likelihoods, we just take the sum. So we just add all these points together, add all these y's together, and that will give us our log likelihood, -165.6257, which is a much easier number to deal with than the e to the -64, which is really small. Now, you might be saying, well, is this the same value? How do I check? Well, you can check by looking at the number of digits. Let's say we want to go to the 8th digit, and we round this sum of the log versus log of the product. And if we add those two together, we find that they are actually the same up to 8 digits, possibly more. It depends on the, it'll depend on the computer itself. So if we want to do this in a single step, we can actually generate a function, which will take the log of each of the observations of x, and then sum them up and return the log likelihood. So now we've got a function, and so we can apply our e to that, and we find out that we get -145.652, which is the same thing. So this function, and doing these two steps separately are the same thing, which is what our function is doing. Now let's define another one, which says, let's take a parameter. Okay, whatever our values are in our x, we're going to apply the mean and standard deviation based on the parameter that we give it. So we make our log likelihood parameter based. We draw a new series, 100 observations. We're going to label that as x. So now we know what x is when it goes into our LLIC function, and we can find out what the total log likelihood is if we give it the true values. Note that these are the same. So if we gave it the true values, we get minus 202.059. And if we use the incorrect mean and standard deviation, what are we going to get? Well, we get minus 322.7922, which is more negative. So this is going to be lower probability, because as log probabilities get smaller and smaller, i.e. more and more negative, the probability is getting smaller and smaller as well. Now let's look at what these two likelihood series look like in a graph. So we need to have a maximum, and we want to have that close to as zero as possible. We want a minimum, and so we plot our first series. There's our log likelihood of our correct series. So this is the series where the mean and standard deviation are correct. And then we're going to add the points in red for the incorrect mean and standard deviation. And you can see that these values are much more negative in this at the tails away from the two. Okay, so we can see that this is much lower. And if you can tell that if you added all the blue ones up, you're adding up things that are between -3 and -5. Whereas if you add up all the reds, you're between -2.5 to almost -15. So these are going to be much more negative, which is why we end up with the -322. So let's apply just using the coefficients, and we can see that our coefficient function worked, giving it the incorrect one. Now this becomes important why you use the coefficients when you actually go into maximum likelihood and other likelihood or maximization or optimization functions, because what you're going to be moving usually is you're going to be moving the parameters around, and the data is going to be static. So what you want to be able to do is move the data around to match what the true values are, or an estimate of the true values. Okay, so that'll be in the maximum likelihood approaches. Great, and we'll see you in the next video.